Hello there, and welcome to Sleepy Mindscape. I'm so glad you wandered here tonight. Maybe your thoughts have been running all day, or maybe you simply love drifting to sleep while exploring the vast unknown. Either way, you've arrived at the right place, a place where science meets stillness and imagination becomes your pillow. So take a deep breath, let your shoulders drop, and feel the weight of the day dissolve into starlight. There's nowhere you need to be, nothing you need to do. Tonight, we're setting sail beyond the clouds, past the moon, past the planets, into the silent ocean of our home galaxy, the Milky Way, a luminous river of stars stretching across the night, woven with dust, light, and time itself. Every shimmer you see out there is a sun with its own story, some young and burning bright, others ancient and fading into memory. As you drift deeper into this cosmic sea, you'll hear about spiraling arms, sleeping giants, and the quiet heartbeat of a supermassive black hole resting at our galactic core. Each whisper, each sound, is a step farther from the noise of the world and closer to the calm infinity of the stars. If these gentle journeys help you find peace, help you breathe a little slower, and dream a little deeper, consider liking and subscribing. It helps other sleepy minds find their way here too, one dreamer at a time. Now, close your eyes. Let your thoughts drift weightless, and together, let's wander through the galaxy. What if I told you that the stars in your night sky aren't actually from our galaxy? Some of the light reaching your eyes tonight comes from ancient suns that were born in completely different galaxies. The galaxies that the Milky Way devoured billions of years ago. These stellar refugees now orbit in our halo, carrying the chemical fingerprints of their destroyed homeworlds. Tonight, as you drift off to sleep, you'll discover the forensic evidence that reveals our galaxy's violent, evolving history. The data shows how astronomers trace stellar streams and analyze ancient star compositions to reconstruct exactly how the Milky Way assembled itself through cosmic conquest. When you look up at the night sky, you see evidence of ancient galactic processes that shaped our cosmic neighborhood. The Milky Way appears peaceful from our perspective here on Earth. The gentle sweep of stars across the darkness suggests order and tranquility, but astronomers have discovered something remarkable hidden within our galaxy's structure. Modern telescopes reveal that our cosmic home bears the traces of billions of years of galactic accretion. Hidden throughout our halo are stellar streams. These thin ribbons of stars wrap around the galaxy like cosmic traceries. They stretch across hundreds of thousands of light years, forming delicate patterns that most people never see. The streams are nearly invisible to the naked eye, requiring sophisticated instruments to detect their faint glow against the background of space. These streams are the stretched-out remains of smaller galaxies that were disrupted by our galaxy's gravity. When a smaller galaxy ventures too close to the Milky Way, our massive gravitational field begins to pull it apart. The process works like taffy being stretched. Stars get yanked away from their original homes and scattered into long, thin trails that follow elliptical orbits around our galaxy. Each stream tells the story of a galactic merger that happened billions of years ago. The width of a stream reveals how massive the original galaxy was. The distribution of stars within the stream shows how the tidal disruption unfolded over time. Some streams are tightly packed, indicating a recent gravitational encounter. Others have spread out into diffuse clouds, evidence of ancient accretion events that occurred when the universe was young. The Sagittarius dwarf galaxy is being tidally stripped right now, leaving a trail of stars across our sky. This small galaxy orbits the Milky Way every few 100 million years. Each time it swings close to our galactic center, our gravity tears away more of its stars. The Sagittarius stream now wraps completely around our galaxy, visible as a faint ribbon of light to sensitive telescopes. We are witnessing gravitational structure formation in real time. Scientists can trace these stellar breadcrumbs to reconstruct exactly how each disruption occurred. They use two independent lines of evidence to identify stellar origins. The kinematics reveal how stars move through space. Their velocities and orbital patterns preserve information about their parent galaxy's destruction. The chemistry shows what each star is made of, elements forged in the specific environment where it formed. Together, these dual signatures allow astronomers to rewind time and understand the accretion process in detail. The process resembles astronomical detective work. Each star in a stream carries information about its original galaxy. The star's age reveals when the parent galaxy formed. Its chemical signature shows what kind of environment it grew up in. Its current position and velocity indicate when and how it was separated from its home. Together, thousands of these stellar witnesses provide testimony about cosmic processes that occurred long before Earth existed. Some streams contain stars that are nearly as old as the universe itself. These ancient suns formed when the cosmos was less than 2 billion years old. Their presence in our halo proves that the Milky Way has been accreting smaller galaxies since very early in cosmic history. The process of galactic accretion shaped our galaxy's structure from the beginning. The streams vary dramatically in their characteristics. Some contain hundreds of thousands of stars, while others hold only a few dozen detectable suns. Some streams are perfectly circular, following neat orbits around our galaxy. Others are highly elliptical, indicating chaotic encounters that flung stars into unstable trajectories. The diversity of stream properties reflects the variety of ways that galaxies can be disrupted. But the most remarkable evidence isn't in these streams. The stellar trails are obvious once you know where to look. They announce themselves clearly to anyone with the right equipment. The real challenge lies in identifying the survivors, the stars that somehow escaped complete destruction and maintained their identity within our galaxy's structure. The chemical fingerprints of ancient stars hold the key to understanding our galaxy's accretion history. Every star carries a unique spectral signature that reveals its birth environment. Stars that formed in the early Milky Way show one pattern of elements. Stars born in smaller, primitive galaxies display completely different chemical compositions. By analyzing these fingerprints, astronomers can identify which stars are native to our galaxy and which are immigrants from disrupted systems. The technique works because different types of galaxies produce different mixtures of chemical elements. Large spiral galaxies, like the Milky Way, have complex chemical enrichment histories. They produce heavy elements efficiently through multiple generations of stellar evolution. Small dwarf galaxies have simpler chemical patterns. They form fewer heavy elements and distribute them less evenly among their stars. When astronomers find stars in our halo with chemical signatures that don't match our galaxy's normal patterns, they know they're looking at refugees from other worlds. These stellar immigrants retained their original chemical fingerprints even after being scattered by gravitational forces. They serve as permanent witnesses to cosmic processes that would otherwise be forgotten. This astronomical detective work reveals that our peaceful spiral galaxy actually grew through systematic accretion of its neighbors. The Milky Way didn't form in isolation as a single, pristine structure. Instead, it assembled by incorporating smaller galaxies over billions of years. Our galaxy's beautiful spiral arms, its massive central bulge, and its extended stellar halo all contain the processed remains of dozens of smaller systems. The evidence shows that galactic accretion was especially intense during the early universe, when galaxies were younger and more closely packed together. Mergers and acquisitions happened frequently. Our galaxy participated actively in this cosmic assembly process. The streams and chemical signatures preserve a detailed record of these ancient events. Modern astronomy has transformed our understanding of how galaxies form and evolve. What once seemed like isolated island universes are now revealed as dynamic systems engaged in constant gravitational interaction. Galaxies grow by incorporating their neighbors. They scatter the remains across vast distances. They preserve the original identities of their components while building larger structures. The night sky that appears so serene actually displays the aftermath of billions of years of cosmic assembly. Every star you see overhead tells a story. Some are native citizens of our galaxy, born from gas clouds that always belonged to the Milky Way. Others carry the chemical memories of their lost homelands, written in the very atoms that make up their cores. These chemical signatures reveal which stars belong to our galaxy and which are immigrants from ancient worlds. Some stars in our galaxy carry the chemical fingerprints of galaxies that no longer exist. These stellar immigrants hold evidence of their origins written in their very atoms. When you understand how to read these cosmic fingerprints, you discover that our galaxy contains refugees from dozens of destroyed galactic communities. When astronomers analyze starlight, they can read the periodic table written in each star's spectrum. Every element produces characteristic wavelengths of light when heated. Hydrogen creates specific spectral lines. Helium produces different patterns. Iron, carbon, oxygen, and dozens of other elements each contribute their unique signatures to a star's light. This spectroscopic analysis works like cosmic forensics. You can determine exactly what elements exist inside a star by studying the light it emits. The process resembles reading a barcode. Each element absorbs and emits light at precise wavelengths. When starlight passes through a spectrometer, it separates into its component colors. Dark absorption lines appear at specific positions, marking where elements in the star's atmosphere have absorbed certain wavelengths. The strength and width of these lines reveal how much of each element exists in the star. Modern telescopes can detect trace amounts of dozens of different elements in stellar atmospheres. They measure not just the presence of elements, but their exact proportions. This creates a detailed chemical inventory for every star astronomers observe. The chemical composition becomes a permanent record of the conditions where that star formed, but some of our halo stars show almost no heavy elements. This chemical composition should be impossible in the modern Milky Way. When astronomers first discovered these metal-poor stars, they created a puzzle that challenged our understanding of galactic evolution. In astronomy, everything heavier than hydrogen and helium counts as a metal. This includes carbon, oxygen, silicon, iron, and all the other elements that make planets and life possible. Stars create these metals through nuclear fusion in their cores. When massive stars explode as supernovas, they scatter these newly created elements into space. Subsequent generations of stars form from gas clouds enriched with these metals. Our galaxy has been producing metals for over 12 billion years. Generation after generation of stars have lived, died, and enriched the interstellar medium with heavy elements. By now, even newly formed stars in the Milky Way contain significant amounts of metals. The chemical evolution of our galaxy should have eliminated stars with truly pristine compositions. Yet scattered throughout our halo are stars with metal contents thousands of times lower than normal Milky Way stars. These hypermetal-poor stars contain almost pure hydrogen and helium, with only trace amounts of heavier elements. They formed in a universe before widespread metal production, when galaxies were smaller and more primitive. Their compositions resemble what you would expect from the very first generation of stars in the universe. These hypermetal-poor stars formed when the early cosmos contained only the elements created during the Big Bang: hydrogen, helium, and tiny amounts of lithium. The first stars formed from this pristine material. They lived, died, and began the process of chemical enrichment. Small galaxies experienced this enrichment process much more slowly than large ones like the Milky Way. Dwarf galaxies have weaker gravitational fields. When their massive stars exploded, the metal-rich gas often escaped into intergalactic space instead of remaining to enrich future star formation. This created environments where stars could form with very low metal content, even billions of years after the Big Bang. Their near-pristine composition proves they were born in different galaxies entirely. The chemical signatures of these stars don't match the enrichment pattern of our galaxy. They preserve the slow, inefficient metal production characteristic of small dwarf galaxies. Finding them in our halo demonstrates that the Milky Way acquired them through mergers and tidal stripping. These hypermetal poor stars are fossils made of light, preserving chemical conditions from soon after the Big Bang, before the Milky Way had fully formed. They maintain their original chemical purity despite being scattered by gravitational forces over billions of years. Unlike gas and dust that gets mixed and processed over cosmic time, stars preserve their birth compositions throughout their lifetimes. These stellar refugees have been orbiting in our halo for billions of years, carrying memories of their destroyed homeworlds. Each hypermetal poor star represents a survivor from an ancient galactic community. These stars formed in small galaxies that had their own unique evolutionary histories. They witnessed the slow buildup of heavy elements in their birth environments. They experienced the tidal forces that eventually tore their home galaxies apart. Now, they drift through our halo as permanent monuments to lost worlds. Each one is a time capsule from the early universe, preserving conditions from when the cosmos was young. Their low metal content provides direct evidence of what star formation was like when galaxies were still small and inefficient at producing heavy elements. They offer glimpses into cosmic environments that no longer exist anywhere in the modern universe. The stars contain information that you can't find any other way. Written observations only extend back a few centuries. Geological records cover billions of years, but only for Earth. These ancient stars provide data about cosmic conditions from over 10 billion years ago, when the universe was less than a quarter of its current age. Studying these stellar time capsules reveals how chemical evolution proceeded in the early cosmos. Different elements were produced at different rates. Some metals appeared quickly when the first massive stars exploded. Others accumulated gradually over many stellar generations. The abundance patterns in hypermetal poor stars map out this ancient timeline. The research shows that star formation in small galaxies followed completely different patterns than in large ones. Small galaxies couldn't retain their metals efficiently. They experienced periods of active star formation, followed by long, quiet phases. Their stellar populations developed unique chemical characteristics that distinguish them from stars born in large spiral galaxies. But chemical composition provides only part of the story. The complete picture requires understanding how these stellar refugees move through space. The way these stars move through space reveals the most dramatic evidence yet of our galaxy's violent assembly. Every star in our galaxy follows a specific orbit determined by the gravitational forces acting on it. Stars that formed in the Milky Way follow predictable orbital patterns. But but stars that originated in other galaxies retain orbital characteristics from their birth environments. Combining chemistry with orbital motion creates the full portrait of our galaxy's acquisition history. The chemical fingerprint identifies which ancient galaxy a star came from, while its orbital pattern reveals exactly how that galaxy was disrupted and absorbed into our cosmic neighborhood. The orbital patterns reveal something even more striking about our galaxy's assembly history. Why would some stars follow retrograde orbits that move against our galaxy's rotation? The question becomes critical when you realize these reversed motions represent a quiet signature of their foreign origin. The vast majority of stars in our galaxy orbit in the same direction, following the Milky Way's rotation like traffic on a cosmic highway. This orderly motion reflects how our galaxy formed from a rotating cloud of gas and dust. As the cloud collapsed under its own gravity, conservation of angular momentum caused it to spin faster and flatten into a disk. The stars that formed from this material naturally inherited the rotation direction of the original cloud. This process works like a figure skater pulling in their arms during a spin. The rotating gas cloud contracts and spins faster, creating the systematic motion we observe today. Nearly all stars in our galactic disk follow this pattern. They orbit the galactic center in the same direction, maintaining the rotational memory of our galaxy's birth. The motion isn't perfectly circular. Stars follow elliptical orbits that carry them closer to and farther from the galactic center over millions of years. But they all maintain the same general direction of travel. This creates the smooth, organized flow that characterizes a mature spiral galaxy. You can observe this orderly motion directly by studying stellar velocities. When astronomers measure how fast stars move relative to the galactic center, they find a clear pattern. Stars in the inner galaxy orbit faster than those in the outer regions, following the gravitational dynamics of a rotating system. The pattern resembles the way planets orbit the sun, with inner objects completing their orbits more quickly than outer ones. But scattered throughout our halo are stars moving in retrograde orbits. These stars move in the opposite direction from our galaxy's normal rotation, creating misaligned motion that travels against the established patterns. The retrograde stars stand out dramatically when you map stellar motions in 3 dimensions. While most halo stars follow complex but generally prograde orbits, the retrograde population creates distinct streams of reversed rotation. These stars seem to ignore the gravitational blueprint that governs normal stellar behavior. Their orbital characteristics differ from normal halo stars in multiple ways. Retrograde stars often follow highly elliptical paths that carry them far from the galactic plane. They reach extreme distances before swinging back toward the galactic center. Their orbital periods can span hundreds of millions of years, much longer than typical disk stars. These backwards travelers make up a significant fraction of our outer halo population. In some regions of the outer halo, Retrograde stars represent nearly half of all observed objects. This isn't a small population of cosmic oddities. The retrograde fraction is large enough to require a systematic explanation. The discovery challenges simple models of galaxy formation. If our galaxy formed from a single collapsing cloud, all stars should rotate in the same direction. The presence of substantial retrograde populations indicates a more complex assembly history. Their reverse motion isn't random. The retrograde stars don't show chaotic or arbitrary velocities. Instead, they display organized motion patterns that suggest common origins. Groups of retrograde stars often share similar orbital characteristics, indicating they arrive together as coherent populations. The key insight comes from understanding galactic mergers. When the Milky Way captured smaller galaxies, some stars retained their original orbital direction. The victim galaxies had their own rotation patterns before being disrupted. Depending on their approach angle and orbital orientation, stars from these galaxies could end up moving backwards relative to our galaxy's rotation. Think of it like merging two highway systems with different traffic flows. When you combine roads carrying traffic in opposite directions, some vehicles will end up traveling against the predominant flow. The stars retain their original motion directions even after their parent galaxies are destroyed. This creates a three-dimensional map of ancient mergers written in stellar motion. Each group of retrograde stars with similar orbital properties likely originated in the same disrupted galaxy. By studying the distribution and characteristics of retrograde populations, astronomers can reconstruct the merger events that built our galaxy. The technique works because gravitational interactions preserve information about orbital origins. When a small galaxy approaches the Milky Way, tidal forces stretch it into streams, but the stars maintain memory of their original velocities. This creates distinct kinematic signatures that persist long after the parent galaxy disappears. Computer simulations confirm this interpretation. When researchers model galaxy mergers, they find that captured stars retain orbital characteristics from their birth environments. Depending on the merger geometry, significant fractions of captured stars can end up in retrograde orbits. Each retrograde star is essentially a cosmic immigrant that never fully assimilated into our galaxy's rotation. They preserve the orbital memory of their destroyed homeworlds. Unlike chemical signatures that can be altered by stellar evolution, orbital characteristics remain essentially unchanged over billions of years. The retrograde populations provide a detailed record of our galaxy's merger history. Different retrograde groups show distinct orbital properties that reflect the characteristics of their parent galaxies. Large retrograde streams indicate major merger events. Smaller groups suggest the disruption of dwarf galaxies or globular clusters. Some retrograde stars follow nearly radial orbits that plunge deep into our galactic center before swinging out to to enormous distances. Others maintain more circular paths, but travel in the wrong direction. The diversity of retrograde orbits reflects the variety of ways that galaxies can be captured and disrupted. The pattern of these backward stars reveals something crucial about how our galaxy grew. The retrograde fraction increases with distance from our galactic center. In the inner halo, most stars follow prograde orbits, but in the outer halo, retrograde stars become increasingly common. This radial gradient indicates that our galaxy assembled through a series of mergers rather than a single formation event. The outer regions contain more captured material from disrupted galaxies. The inner regions are dominated by stars that formed within our galaxy's original structure. The retrograde stars demonstrate something remarkable about galactic dynamics. The Milky Way doesn't hold together based on simple Newtonian physics alone. Our galaxy turns like a solid wheel because of dark matter and visible matter constraints that create complex gravitational architecture. Yet these retrograde stars defy even those classical expectations, requiring a merger history explanation to account for their reversed motion. They prove that the Milky Way didn't form as a single, pristine spiral. Instead, our galaxy assembled itself piece by piece through cosmic cannibalism. The retrograde stars are living fossils of this violent assembly process. They demonstrate that galaxy formation involves complex merger histories rather than simple collapse scenarios. The stars with reversed rotation in our halo carry the orbital memory of dozens of destroyed worlds. Each retrograde star represents a refugee that maintained its original trajectory despite being scattered by gravitational forces. Together, they provide direct evidence that our galaxy grew through conquest rather than isolation. These stellar immigrants preserve not just their chemical signatures, but also their kinematic fingerprints, creating a comprehensive record of ancient galactic encounters that shaped our cosmic neighborhood. Astronomers can now map these ancient encounters with unprecedented precision. The Gaia spacecraft has transformed our understanding of the galactic halo from what was once thought to be a smooth sphere of old stars into a complex archaeological site filled with substructures. Early observations suggested a simple structure. Astronomers expected to find old stars distributed evenly around our galaxy in a roughly spherical pattern. This would match theoretical models of how galaxies form from collapsing gas clouds. The data shows something completely different. The Gaia mission has created a census of over 1 billion stars, measuring their positions, distances, and motions with precision that seemed impossible just decades ago. Gaia can detect stellar motions as small as walking speed at the distance of the Moon. This European Space Agency spacecraft has revealed that our halo contains dozens of distinct substructures, each representing a different merger event. Instead of smooth distributions, our halo is filled with organized remains. These features have names that sound like architectural elements: shells, streams, and clumps, but they represent the fossil remains of galactic accretion rather than peaceful construction. Each substructure represents the remnants of a different merger event. When you map the three-dimensional positions of halo stars, distinct patterns emerge. Some stars form long, narrow streams that wrap around our galaxy. Others cluster into shell-like structures at specific distances from the galactic center. Still others gather in dense clumps that orbit through the outer regions. These patterns don't occur randomly. Gravitational interactions create specific signatures when galaxies merge and disrupt. Computer simulations show how tidal forces stretch smaller galaxies into characteristic shapes. The stretched remains form streams. The compressed debris creates shells. The surviving cores become clumps. The spacecraft's data reveals structure. Everywhere astronomers look, features that were invisible to previous surveys now stand out clearly in three-dimensional maps. The complexity resembles a cosmic jigsaw puzzle with pieces from many different boxes. The discovery has revealed that our galaxy isn't even perfectly flat. The Milky Way's disk is warped, bending upward on one side and downward on the other, forming a graceful wave pattern. This warping isn't just visible in stellar streams. Radio telescopes mapping hydrogen gas show how the entire galactic structure responds to invisible forces. Satellite galaxies tug gently on our disk, creating these large-scale deformations that extend across hundreds of thousands of light years. The warp demonstrates how our galaxy continues to be shaped by gravitational interactions with its neighbors. Some streams are still tightly wound, indicating recent mergers. These features show clear organization and distinct boundaries. The stars within these streams share similar velocities and chemical compositions. Their tight clustering indicates they were disrupted relatively recently in cosmic terms, within the last few billion years. The recently disrupted streams provide the clearest evidence of ongoing galactic cannibalism. You can trace individual streams from one side of our galaxy to the other. Some wrap completely around the Milky Way multiple times, creating complex three-dimensional patterns. The stars in these streams maintain their original velocities from before the disruption. Meanwhile, others have spread into diffuse shells. These older features show the effects of billions of years of gravitational mixing. The stars have been scattered by repeated interactions with our galaxy's gravitational field. What once were tight streams have evolved into broad, shell-like distributions. The transition from streams to shells follows predictable patterns. Newly created streams are narrow and well-defined. Over time, gravitational perturbations cause the streams to broaden and lose their original structure. Eventually, they merge into the general halo population, becoming nearly indistinguishable from the background. Scientists can use computer simulations to reconstruct these ancient disruptions. The technique works like cosmic archaeology. Researchers input the current positions and velocities of stars in a substructure. run gravitational dynamics calculations to determine the victim galaxy's original path, size, and disruption timeline. This robust approach allows astronomers to solve cosmic cold cases billions of years old. The simulations reveal the original properties of the disrupted galaxies. Models can determine how massive the victim galaxy was when the disruption occurred and what orbital trajectory it followed. Some disrupted galaxies were surprisingly large, containing billions of stars before being torn apart. The computer models also predict where to find additional debris from known merger events. When a galaxy gets disrupted, its stars scatter along predictable trajectories. Simulations can forecast where these scattered stars should be located today. Observers then search those regions and often find exactly the predicted stellar populations. Different types of mergers create different types of substructures. Major mergers involving large galaxies create massive streams and shells that dominate entire regions of the halo. Minor mergers with small dwarf galaxies produce more modest features that require careful observation to detect. The substructures also preserve information about the orbital dynamics of ancient mergers. Stars from galaxies that approached on radial orbits create different patterns than those from galaxies with circular trajectories. The three-dimensional geometry of each substructure encodes the merger history in permanent form. The technique works because stellar orbits preserve information indefinitely. Unlike gas, which gets mixed and reprocessed, stars maintain their trajectories for billions of years. This creates a permanent record of merger events that occurred throughout cosmic history. The ongoing discoveries demonstrate that galactic archaeology has become a mature science. Astronomers can now routinely identify merger debris and reconstruct the properties of the original victim galaxies. The field combines observational astronomy with theoretical modeling to create detailed reconstructions of ancient cosmic encounters. The archaeological evidence shows that our galaxy has been remarkably successful at acquiring smaller neighbors. The number of detected substructures continues to grow as observational techniques improve. Each new survey reveals additional merger signatures hidden in our halo. The pattern reveals that major mergers happened regularly throughout our galaxy's history, with some periods showing particularly intense activity. This timeline reveals something remarkable about galactic evolution. There was a period in our galaxy's youth when it went on an unprecedented growth spurt. The evidence lies scattered throughout our halo in the form of ancient stars that all tell the same story. They point to a time when the Milky Way transformed from a modest spiral into the massive galaxy we see today. By studying the ages and compositions of halo stars, astronomers have reconstructed our galaxy's merger timeline. The technique works like carbon dating, but on a cosmic scale. Stars preserve chemical signatures from their birth environments throughout their entire lifetimes. By analyzing thousands of these stellar time capsules, researchers can determine when major merger events occurred. The process requires measuring precise abundances of multiple elements in each star's atmosphere. Different types of galaxies produce distinct chemical patterns based on their star formation histories. Large galaxies create complex element mixtures through multiple generations of stellar evolution. Small galaxies show simpler patterns with fewer heavy elements. When astronomers map these chemical signatures against stellar ages, clear patterns emerge. Groups of stars with similar ages and compositions cluster together in the data. These clusters represent the debris from individual merger events. The technique allows researchers to identify not just when mergers occurred, but also the characteristics of the victim galaxies. The evidence points to a dramatic period about 10 billion years ago, when the Milky Way experienced its most violent growth phase. Multiple independent lines of evidence converge on this time frame. The chemical compositions of ancient halo stars show a sudden increase in metal content. The age distribution of thick disk stars shows enhanced star formation during this period. The orbital characteristics of halo populations all point to major disruptions around this time. This wasn't a gradual process spread over billions of years. The merger timeline shows a concentrated burst of activity that lasted perhaps 2 billion years. During this relatively short cosmic timespan, our galaxy doubled or tripled in mass through a series of major acquisitions. During this era, multiple large galaxies were consumed in rapid succession, fundamentally reshaping our galaxy structure. Computer simulations show that merging several substantial galaxies within a short time frame creates completely different outcomes than isolated merger events. The rapid succession prevented our galaxy from settling into equilibrium between mergers. Each merger event triggered massive disruptions that were still ongoing when the next victim arrived. This created a period of sustained chaos where our galaxy's structure was constantly being reshaped. The normal processes of disk formation and spiral arm development were repeatedly interrupted by gravitational violence. The merger cascade worked like a cosmic growth phase. Once our galaxy reached a certain critical mass, it became gravitationally dominant in its local environment. Smaller galaxies that had previously maintained stable orbits suddenly found themselves pulled into death spirals. The process accelerated as our galaxy's growing mass increased its ability to capture additional victims. This ancient growth period deposited enormous numbers of stars into our halo and thick disk. The stars from disrupted galaxies didn't simply disappear or merge seamlessly into our existing structure. Instead, they created entirely new components of our galaxy that persist to this day. The thick disk, which lies between our thin disk and halo, formed primarily during this merger epoch. This structure is older, puffier, and more diffuse than our thin disk. Its stars exhibit highly tilted and elliptical orbits that suggest they were stirred by early galactic collisions. Over time, the these scattered populations settled into the thick disk structure we observe today. Similarly, the stellar halo gained most of its current population during this period. The halo contains roughly 1% of our galaxy's total stellar mass, but nearly all of these stars originated in other galaxies. The ancient merger period populated our halo with stellar refugees from dozens of destroyed worlds. The Gaia-Enceladus merger was particularly massive, contributing roughly half of our current halo population. This single merger event was one of the largest acquisitions in our galaxy's history, involving a galaxy with perhaps 10 billion stars. The disrupted galaxy's stars now form a major component of our inner halo. The Gaia-Enceladus debris shows distinct chemical and kinematic signatures that distinguish it from other halo populations. Its stars follow characteristic orbital patterns that reflect their violent incorporation into our galaxy. The sheer number of stars from this single merger demonstrates the scale of ancient galactic violence. Archaeological evidence from this merger appears throughout our galaxy. The thick disk contains substantial populations of Gaia-Enceladus stars. The inner halo shows clear chemical signatures from the disrupted galaxy. Even some globular clusters may have originated in the Gaia-Enceladus system before being captured by our galaxy. These mergers didn't just add stars. The gravitational disruptions completely reorganized our galaxy's architecture. Before the merger epoch, our galaxy likely resembled a smaller spiral with a thin disk and modest bulge. The ancient collisions transformed it into the complex, multi-component system we inhabit today. The mergers created our galaxy's massive stellar halo, which extends far beyond the visible disk. They thickened our disk by scattering stars into higher orbits. They may have triggered the formation of our central bar structure through gravitational instabilities. The entire architecture of the modern Milky Way reflects the consequences of ancient violence. The violence of these collisions heated up our galaxy's disk and scattered stars into more chaotic orbits. When galaxies merge, gravitational interactions increase the random motions of stars. This process, called dynamical heating, transforms orderly disk structures into more spherical distributions. Our thick disk shows clear evidence of this heating process. Its stars have much higher random velocities than thin disk populations. They follow more elliptical orbits that carry them farther from the galactic plane. The heating signatures preserve a record of the gravitational violence that created these populations. The disk heating also affected star formation patterns throughout our galaxy. The gravitational disruptions compressed gas clouds and triggered bursts of new star formation. This created the enhanced stellar populations that characterize the thick disk. The chemical compositions of these stars reflect the chaotic conditions during the merger epoch. But this ancient growth period had an unexpected consequence for our galaxy's future. The same violent processes that built our galaxy also created protective structures that now shield us from additional major disruptions. The merger epoch transformed our galaxy from a vulnerable target into a gravitational fortress. The massive halo, built from the wreckage of other worlds, now acts as a gravitational shield against future mergers. The scattered debris of ancient victims has become our cosmic armor, deflecting potential threats and ensuring our galaxy's continued stability. This complex architecture represents the mature phase of galactic evolution, where the violent assembly process has created the very structures that maintain long-term stability. Yet even in this mature phase, our galaxy continues to encounter smaller neighbors that venture too close to our gravitational influence. The Magellanic Clouds demonstrate this process unfolding before our eyes. Right now, two galaxies are approaching our borders, and we can watch their tidal disruption in real time. The process unfolds over millions of years, but modern telescopes capture each stage of the cosmic encounter. We have front-row seats to galactic merger dynamics happening in our immediate neighborhood. The large and small Magellanic Clouds appear as peaceful companions in our southern sky. To observers in the southern hemisphere, these fuzzy patches of light look like detached pieces of the Milky Way. They shine with the combined glow of billions of stars, creating distinctive landmarks in the night sky. Ancient cultures incorporated them into their mythologies as celestial rivers or cosmic animals. These companion galaxies orbit our galaxy at distances of roughly 160,000 and 200,000 light years, respectively. They appear close enough to seem like permanent fixtures. The large Magellanic Cloud contains about 30 billion stars, while the small Magellanic Cloud holds roughly 3 billion. Both galaxies actively form new stars, filling their spiral arms with bright blue giants and glowing nebulae. Their proximity makes them ideal laboratories for studying galactic evolution. Astronomers can resolve individual stars in both galaxies, measuring their properties with precision impossible for more distant systems. The Magellanic Clouds have provided crucial insights into stellar evolution, supernova explosions, and the formation of massive star clusters. But these aren't permanent satellites orbiting safely at constant distances. Recent measurements of their motions reveal a more dramatic truth. Both galaxies follow highly elliptical trajectories that carry them alternately closer to and farther from our galaxy. Their orbits are unstable and decaying over cosmic time. The gravitational dance between three massive objects creates complex orbital dynamics. Our galaxy exerts the dominant gravitational influence, but the two Magellanic Clouds also affect each other's motion. This three-body interaction leads to chaotic orbital evolution that makes precise, long-term predictions difficult. They are on a collision course that will end in their complete tidal disruption. Computer simulations show that both galaxies will spiral inward over the next several billion years. Each close passage strips away more of their outer stars and gas. Eventually, they'll merge completely with our galaxy's disk and halo. The process resembles a cosmic death spiral. Each orbital passage brings the galaxies closer to our galactic center. Tidal forces stretch and distort their structures. Stars get pulled away from their home galaxies and scattered into long streams around our galaxy. The disruption has already begun in observable ways. The Magellanic Stream, a ribbon of hydrogen gas stretching over hundreds of thousands of light years, shows they're already being torn apart. This enormous trail of gas extends across 200 degrees of sky when viewed from Earth. The stream contains roughly 1 billion solar masses of hydrogen, representing material stripped from both galaxies. The Magellanic Stream provides direct evidence of ongoing tidal stripping. As the Magellanic Clouds orbit our galaxy, our stronger gravitational field pulls gas away from their outer regions. This material forms a trailing wake that marks their orbital path through space. The immense scale of this stream reveals the extent of the tidal forces acting on both clouds. Radio telescopes can map the stream's structure in detail. The gas shows systematic motion patterns that trace the orbital history of both galaxies. Different parts of the stream originated during different close passages, creating a timeline of the stripping process. The stream also reveals the complex gravitational interactions between all three systems. The gas doesn't follow a simple trailing pattern. Instead, it shows branches and substructures that reflect the gravitational influence of both Magellanic Clouds on the escaping material. Their gravitational interaction with our galaxy has warped our outer disk and triggered new episodes of star formation. The approaching galaxies don't just passively orbit our system. Their gravity creates waves and distortions in our galaxy's outer regions. These perturbations compress gas clouds and trigger bursts of star formation in our disk. The interaction works like dropping stones in a calm pond. The gravitational influence of the Magellanic Clouds creates ripples that propagate through our galaxy's structure. These waves can trigger star formation hundreds of thousands of light years from the galaxies themselves. Observations show enhanced star formation rates in regions of our outer disk that align with the Magellanic orbital plane. Young star clusters and active star-forming regions appear more frequently in areas where the gravitational perturbations are strongest. Computer models predict they'll spiral inward over the next few billion years, eventually merging with our disk. The simulations track the orbital evolution under the influence of dynamical friction. As the galaxies plow through our galaxy's halo, they transfer momentum to the surrounding stars and dark matter. This process gradually slows their orbital motion and causes them to spiral inward. The merger timeline depends on uncertain factors like the mass distribution of our galaxy's dark matter halo. Different models predict collision times ranging from 2 to 8 billion years from now. But all simulations agree that complete merger is inevitable. When the merger occurs, it will dramatically reshape our galaxy's structure. The large Magellanic Cloud contains enough mass to trigger significant changes in our disk, and spiral arm patterns. The collision may even induce a period of enhanced star formation, similar to what we observe in interacting galaxy pairs. This ongoing interaction is actively reshaping our galaxy's outer regions right now. The process isn't waiting for some future collision. The gravitational effects operate continuously as the galaxies orbit our system. Each passage leaves our galaxy slightly different than before. We're witnessing the same process that created our halo streams, but happening in the present day. The stellar streams in our halo formed through identical mechanisms billions of years ago. The Magellanic Clouds demonstrate that galactic cannibalism continues in the current epoch. The key difference is timing. We can observe the Magellanic disruption process in real time rather than reconstructing it from ancient stellar fossils. This provides unprecedented insight into how galaxy mergers actually proceed. The Magellanic Clouds represent the immediate, ongoing nature of smaller scale mergers happening right now. While these encounters reshape our galaxy's outer regions and add material to our halo, they pale in comparison to what awaits us in the distant future. A much more massive encounter approaches through space, one that will dwarf the gentle consumption of these companion galaxies and fundamentally transform our cosmic neighborhood. In 4.5 billion years, our galaxy will experience its final and most dramatic transformation. The event will dwarf every merger we've discussed so far. The approaching collision will end the Milky Way's existence as an independent spiral galaxy and reshape the local universe in ways that seem almost incomprehensible. The Andromeda Galaxy appears as a faint smudge in our night sky, but it's actually racing toward us through space. You can spot this galaxy with the naked eye on clear, dark nights as a hazy patch in the constellation Andromeda. Most people who see it don't realize they're looking at an entire galaxy containing over 1 trillion stars. The light reaching your eyes left Andromeda 2.5 million years ago, when early humans were just beginning to use stone tools. Andromeda spans 6 times the apparent width of the full moon in our sky. If your eyes could see all the galaxy's faint outer regions, it would appear enormous overhead. The galaxy's true size becomes apparent only in long exposure photographs that capture its extended spiral arms and outer stellar halo. The galaxy approaches us at roughly 250,000 miles per hour. This velocity represents the combined motion of both galaxies through space, plus our mutual gravitational attraction. The speed sounds enormous, but crossing the 2.5 million light-year gap between us requires billions of years of steady approach. Precise measurements using the Hubble Space Telescope confirm that collision is inevitable. Earlier observations couldn't determine whether Andromeda would hit us directly or pass by at a safe distance. The uncertainty came from measuring tiny changes in the galaxy's position across the sky. Recent data shows that Andromeda's sideways motion is essentially zero, meaning it's heading straight for us. This isn't just another minor merger. These are two vast, comparable spiral galaxies that will completely reshape both systems through gravitational warping. The collision will involve roughly 1.5 trillion stars from both systems. The gravitational forces released will be unlike anything our galaxy has experienced since its formation. Computer simulations show the collision will fling stars into vast tidal tails stretching millions of light years. The gravitational interaction will stretch both galaxies like taffy being pulled apart. Long streamers of stars will arc out into intergalactic space, creating structures visible from billions of light years away. The simulations reveal a complex dance of destruction and creation. The first close passage will distort both galaxies dramatically. Spiral arms will be stretched and warped beyond recognition. Stars will be scattered into chaotic orbits that bear no resemblance to their original paths. Stars will almost never hit each other during this cosmic collision. The distances between individual stars are so vast that direct collisions remain extremely unlikely, even during galactic mergers. But their immense gravity will warp and fold the galaxies into long, stretching arcs, completely reorganizing the structure of both systems without destroying the stars themselves. After the initial encounter, the galaxy cores will swing apart and approach each other again. This process may repeat several times over hundreds of millions of years. Each passage will further scramble the stellar populations and redistribute mass throughout the merging system. Our solar system will likely survive, but it will be scattered to a completely different region of the merged galaxy. The sun and planets form such a tightly bound system that external gravitational forces can't easily disrupt them. We'll maintain our orbital relationships while being flung to entirely new cosmic neighborhoods. The simulations suggest our solar system has roughly equal chances of ending up in different parts of the merged galaxy. We might find ourselves in the dense central regions, the sparse outer halo, or one of the extended tidal tails. Each location would provide dramatically different night skies for any future observers. The collision will trigger massive bursts of star formation as gas clouds collide and compress. When the galaxy's gas reservoirs interact, they'll create shock waves that compress interstellar material. These compression events will trigger the formation of millions of new stars across both systems. The star formation will be unlike anything occurring in either galaxy today. The collision will create conditions similar to the most active star-forming galaxies in the early universe. Massive star clusters will form at unprecedented rates, filling the merged system with brilliant young stars and glowing nebulae. Both galaxies' supermassive black holes will eventually spiral together and merge in a violent release of gravitational waves. Our galaxy's central black hole contains roughly 4 million solar masses. Andromeda's central black hole is significantly more massive. When these titans merge, they'll create gravitational wave signals detectable across the observable universe. The black hole merger represents the culmination of the entire collision process. The two massive objects will spiral inward through a process called gravitational wave radiation. As they orbit each other at increasing speeds, they'll emit gravitational waves that carry away energy and cause the orbit to decay. The final moments of the black hole merger will release more energy in gravitational waves than all the stars in both galaxies emit in light. The merged black hole will likely recoil from the asymmetric gravitational wave emission, potentially ejecting it from the galaxy center entirely. The final product will be a single larger system that astronomers have already nicknamed Milky Way. This giant elliptical galaxy will contain all the stars from both original galaxies arranged in a roughly spherical distribution. The beautiful spiral patterns that define both current galaxies will be permanently erased, showing the true transformation of the galaxy's structure. Milky Way will be one of the largest galaxies in our local cosmic neighborhood. Its mass will exceed 2.5 trillion solar masses, making it comparable to the most massive elliptical galaxies observed in the current universe. The merged galaxy will gravitationally dominate our local group of galaxies. But this future merger reveals something profound about what galaxies really are. The collision demonstrates that even the largest and most stable appearing structures in the universe are temporary arrangements. Galaxies that seem permanent on human timescales are actually dynamic systems in constant flux. They're not permanent, pristine structures. Galaxies represent temporary arrangements of matter in an endless cycle of cosmic recycling. The atoms that make up our galaxy have been parts of other galaxies throughout cosmic history. They'll continue this cycle long after our current galaxy ceases to exist. Every galaxy in the universe is either eating smaller neighbors or waiting to be consumed by larger ones. This process of cosmic cannibalism represents one of the fundamental mechanisms driving galactic evolution. The Milky Way Andromeda collision simply represents our turn to be recycled into something new and different. The evidence for all these ancient encounters and future collisions lies scattered throughout our current galaxy, waiting for astronomers to piece together the complete story of cosmic conquest and survival. Modern telescopes can read these stellar archives with unprecedented precision, revealing the complete merger history written in our galaxy structure. Our galaxy keeps a detailed record of every world it has ever consumed. The evidence exists in plain sight, scattered throughout our stellar halo in the form of ancient suns that carry permanent records of their origins. Modern astronomy has become a form of galactic archaeology, using stellar populations to reconstruct merger histories. The approach works like criminal forensics applied to cosmic scales. Astronomers collect evidence from crime scenes that occurred billions of years ago, analyzing stellar witnesses that preserve testimony about events no human will ever observe directly. The key insight comes from understanding that that stars act as permanent time capsules, unlike gas and dust, which mix and change composition over cosmic time. Individual stars maintain their original chemical signatures throughout their lifetimes. This preservation creates an unalterable record of galactic merger events that can be read billions of years after the original galaxies disappeared. Each absorbed galaxy left behind a unique signature in the ages, orbits, and chemical compositions of its stars. The orbital signatures provide distinctive fingerprints, while chemical compositions reveal the specific environments where stars formed. Scientists can now identify individual merger events and even estimate the mass and structure of the original victim galaxies. The forensic approach requires corroborating evidence from multiple independent sources. Chemical compositions must match expected patterns for specific types of galaxies. Stellar ages must be consistent with known merger timelines. Orbital characteristics must align with computer simulations of galactic disruption. When multiple lines of evidence converge, they build convincing cases for individual merger events. But the sheer volume of ancient mergers creates significant detection challenges. The most recent mergers preserve clear orbital signatures because their stellar debris hasn't had time to mix thoroughly with our galaxy's background population. Older mergers present a different problem entirely. Their orbital patterns have been scrambled by billions of years of gravitational mixing, making them much harder to identify. The most ancient mergers are the hardest to detect because their signatures have been scrambled by billions of years of gravitational evolution. Repeated interactions with our galaxy's gravitational field gradually randomize stellar orbits. Stars that once followed coherent streams get scattered into more spherical distributions that blend with the general halo population. Chemical signatures resist mixing more effectively than orbital patterns. Gravitational forces can scatter stars into new orbits, but cannot change their internal compositions. The most ancient merger events remain detectable through chemical archaeology, even when their orbital signatures have been completely erased. The key lies in hypermetal-poor stars scattered throughout our halo. These ancient suns contain almost pure hydrogen and helium, with metal contents thousands of times lower than normal Milky Way stars. They preserve their chemical composition even after billions of years of orbital mixing, proving the depth of our galaxy's merger history. These stellar fossils formed in small, primitive galaxies that were disrupted early in cosmic history, when the universe contained fewer heavy elements. These hypermetal-poor stars cluster in the outer regions of our halo, where mixing processes work most slowly. They follow highly elliptical orbits that carry them far from our galactic center. Their extreme chemical compositions make them easy to identify once you know their characteristic signatures. Each one represents a survivor from an ancient galactic community that was consumed billions of years ago. The distant halo structures preserve additional evidence of ancient mergers. Stellar streams and shells in the outer halo often represent the oldest merger debris in our galaxy. These features have survived billions of years of evolution because they orbit in regions where gravitational perturbations are minimal. But even the oldest events leave traces in the most metal-poor stars and the most distant halo structures. The technique can identify merger debris from galaxies that were disrupted over 10 billion years ago. The most metal-poor stars in our galaxy almost certainly originated in small, primitive galaxies that were disrupted early in cosmic history. This forensic approach has revealed something remarkable about our galaxy's appetite. The analysis shows that the Milky Way has consumed dozens of smaller galaxies throughout its history. But identifying all these merger events requires increasingly sophisticated techniques and enormous stellar datasets. The data analysis resembles solving a cosmic jigsaw puzzle with millions of pieces, where each star represents a single piece of evidence. The Milky Way has been surprisingly efficient at completely digesting its victims, erasing most evidence of their original identities. The galaxy's gravitational field acts like a cosmic blender, mixing absorbed material with existing populations. Over billions of years, this process makes it increasingly difficult to distinguish native stars from stellar immigrants. Only the most careful analysis can now distinguish the scattered remains of dozens of ancient worlds. Each new generation of telescopes and analysis techniques reveals additional merger signatures that were previously undetectable. The fossil record grows more complete as astronomers develop better methods for reading the stellar archives preserved in our halo. The evidence shows that galactic cannibalism has been the dominant process shaping our galaxy's evolution. The systematic absorption of smaller neighbors built our massive halo, thickened our disk, and created the complex multi-component structure we observe today. The forensic reconstruction reveals a galaxy that grew through conquest rather than peaceful assembly. But this archaeological investigation has also revealed something unexpected about the cosmic battlefield surrounding our galaxy. The merger record shows clear patterns in what types of galaxies get consumed and when these encounters occur. Not every approach results in complete destruction. Several galaxies have managed to avoid this fate entirely, forming what astronomers call the Survivors Club. These resilient systems tell a different story than the stellar streams and fossil remains we've been examining. They demonstrate that galactic interactions don't always end in complete annihilation. Some galaxies possess structural characteristics that allow them to endure multiple close encounters with our massive gravitational field. These survivors challenge the simple narrative of galactic cannibalism, where large galaxies always consume smaller ones. The survivors show that galaxy interactions can be more complex than pure predator-prey relationships. Their continued existence provides crucial insights into the specific factors that separate survival from destruction. The key to understanding galactic survival lies in examining the structural characteristics that separate survivors from victims. Size matters, but it's not the only factor determining a galaxy's fate. Internal structure, orbital trajectory, and timing all influence whether a galaxy gets completely destroyed or manages to persist as a diminished but coherent system. The Sagittarius dwarf has lost most of its mass, but still maintains a coherent core after multiple close passages. This small galaxy orbits our galaxy every few 100 million years. Each orbital passage strips away more of its outer stars and gas. The galaxy has lost roughly 90% of its original mass over billions of years of tidal harassment. Despite this massive loss, the Sagittarius dwarf persists as an identifiable structure. Its central regions contain enough stars to maintain gravitational cohesion. The galaxy's core density allows it to resist complete tidal disruption, even during close approaches to our galactic center. The survival process works like cosmic erosion. Each orbital passage removes the galaxy's loosely bound outer layers while leaving the dense central core intact. Over time, the galaxy shrinks, but doesn't disappear entirely. The remaining core becomes increasingly resistant to further stripping as its stellar density increases. Observations show that the Sagittarius dwarf continues to form new stars despite its ongoing destruction. The galaxy's remaining gas clouds still collapse to create stellar nurseries. This ongoing star formation proves that the galaxy retains enough internal structure to support complex astrophysical processes. The most successful survivors share certain structural characteristics that help them resist tidal disruption. The survivors often maintain tight stellar cores that resist complete tidal stripping while exterior mass is peeled away. These dense central concentrations of stars create gravitational anchors that hold the galaxy together during close encounters. Orbital mechanics also plays a crucial role in determining survival odds. Galaxies that follow circular orbits at large distances experience gentler tidal forces than those on highly elliptical trajectories. The survivors often maintain orbital paths that minimize their exposure to our galaxy's strongest gravitational fields. Galaxies with the right combination of internal structure and orbital characteristics can survive repeated encounters that would destroy less well-protected systems. The survivors represent the galaxies that developed resilient configurations against gravitational predation. Some surviving galaxies follow orbital resonances that prevent them from approaching too closely to our galactic center. These stable orbital configurations create protection zones where smaller galaxies can maintain safe distances from our most destructive gravitational forces. Others have been stripped down to their most essential components, but continue to exist as ultra-faint dwarf galaxies. These systems represent the extreme end of galactic survival. They contain only thousands or tens of thousands of stars, making them barely detectable with current ultra-faint dwarf galaxies may be the most common type of galaxy in the universe, but they are difficult to find because they contain so few stars. Recent surveys have discovered dozens of these systems orbiting our galaxy. Each one represents a survivor that lost almost everything, but managed to retain enough mass to remain gravitationally bound. Yet their persistence suggests they are held together by large amounts of dark matter that provides the necessary additional gravitational binding. The ultra-faint systems challenge our understanding of the minimum mass required to form and maintain a galaxy. Some contain so few stars that random motions should disperse them over cosmic time. These survivors provide crucial information about the merger process and the conditions that determine a galaxy's fate. Studying them reveals which factors allow galaxies to resist complete destruction. The research helps astronomers understand why some encounters result in total absorption, while others leave identifiable remnants. The survivors serve as natural laboratories for testing theories about galaxy formation and evolution. They preserve information about the early universe when small galaxies were more common. Their chemical compositions and stellar populations provide insights into how galaxies evolved under different environmental conditions. Comparing survivors with completely disrupted systems reveals the critical thresholds that separate survival from destruction. The analysis shows that galaxy mass, internal structure, and orbital characteristics all contribute to determining the outcome of galactic encounters. Their continued existence proves that galactic interactions aren't always fatal. Sometimes they're transformative. The survivors demonstrate that galaxy evolution involves more than simple growth through mergers. Some systems adapt to hostile environments by shedding mass while retaining their fundamental identity. The transformation process creates new types of galactic structures that don't fit traditional classification schemes. Heavily stripped dwarf galaxies occupy a middle ground between intact systems and completely disrupted stellar streams. They represent intermediate stages in the galaxy destruction process. But studying these survivors has revealed something significant about our galaxy's future. The analysis shows patterns that extend beyond individual survival stories. The distribution and characteristics of surviving galaxies provide insights into the broader evolution of our galactic neighborhood. The local group contains a finite number of galaxies, and we've already absorbed or disrupted many of the largest accessible systems. The remaining survivors represent increasingly marginal targets for future mergers. The evidence suggests our galaxy has consumed most of the readily available smaller prey in its vicinity. The Milky Way is entering a new phase of its evolution, where dramatic growth through major mergers becomes increasingly rare. The era that built our massive halo and complex structure is winding down as our galaxy reaches gravitational maturity in its local environment. The patterns in our local cosmic neighborhood reveal a different phase beginning. Our galaxy's age of violent expansion is gradually coming to an end. The evidence appears in multiple forms throughout the Milky Way, from declining star formation rates to the empty spaces where prey galaxies once orbited. What we're witnessing represents a fundamental transition in our galaxy's evolutionary timeline. The Milky Way has settled into its middle age, transforming from rapid growth to a mature spiral, glowing gently in its current phase. The galaxy still forms stars, but no longer in a hurry. Modern observations show that our galaxy creates new stars at roughly half the rate it maintained during its peak activity several billion years ago. The decline follows a predictable pattern observed in massive spiral galaxies throughout the universe. Star formation requires raw materials in the form of cold gas clouds that can collapse under their own gravity. Our galaxy contains finite reserves of this material, and we've been converting it into stars for over 12 billion years. The process works like burning through a fuel supply that gets replenished more slowly than it gets consumed. The decline isn't uniform across our galaxy structure. The central regions show the most dramatic reduction in star formation activity. The spiral arms maintain higher rates of stellar birth, but even these active regions produce fewer new stars than they did in the past. The outer disk regions have essentially stopped forming stars entirely in many locations. Measurements of stellar ages reveal this timeline clearly. The youngest stars cluster in specific regions, while vast areas of our galaxy contain no recently formed objects. The age distribution shows that our galaxy's most productive stellar factories operated billions of years ago rather than today. This decline reflects more than just fuel consumption. The gravitational dynamics that once triggered intense star formation have settled into more stable configurations. Our galaxy's disk has reached an equilibrium where dramatic disturbances occur less frequently. The spiral density waves that compress gas clouds into star-forming regions have weakened over time. The slowdown stems from two primary factors. Our galaxy contains substantial reserves of hydrogen that could theoretically support continued star formation for many more billions of years. The problem lies in the accessibility and distribution of this material rather than its total abundance. But equally important, the merger process that once provided regular injections of fresh gas and triggered bursts of star formation has become increasingly rare. We're running out of small galaxies to consume. The local group contains only a finite number of dwarf galaxies, and we've already absorbed many of the largest accessible targets in our immediate neighborhood. When astronomers catalog the remaining dwarf galaxies in our vicinity, they find mostly small, low-mass systems that would provide relatively modest contributions to our galaxy's growth. The largest remaining targets include the Magellanic Clouds, which we've already discussed as future merger candidates. Beyond these systems, our local environment contains perhaps 24 smaller dwarf galaxies. Most of these contain fewer stars than a single large star cluster in our galaxy's disk. This represents a dramatic change from conditions during our galaxy's youth. The early universe contained much higher densities of small galaxies in every region. The local group once held dozens of substantial systems that have since been consumed or dispersed. We're approaching the point where we've essentially cleared out our immediate neighborhood. Future mergers will be smaller and less dramatic than the ancient feeding frenzy that built our halo. The remaining dwarf galaxies will provide modest additions to our stellar population rather than the transformative events that shaped our galaxy's structure billions of years ago. The scale difference becomes clear when you compare future and past mergers. The Gaia-Enceladus event that we discussed earlier involved a galaxy containing perhaps 10 billion stars. The remaining dwarf galaxies in our local environment typically contain only millions or hundreds of millions of stars. The impact on our galaxy's evolution will be correspondingly smaller. These minor mergers will continue to occur over many billions of years, but they won't trigger the dramatic restructuring events that characterized our galaxy's violent youth. Instead, they'll add modest populations to our halo and outer disk without fundamentally altering our galaxy's architecture. Our galaxy is becoming gravitationally dominant in our local neighborhood, creating a zone of stability. Our massive dark matter halo now extends far enough to influence the motion of galaxies throughout the local group. This gravitational dominance prevents new systems from approaching our galaxy with the high velocities that once triggered violent mergers. The process works like establishing territorial control over a large region. Smaller systems that enter our gravitational influence sphere get captured into stable orbits rather than plunging directly toward our galactic center. This creates a buffer zone that protects us from future major disruptions. The gravitational influence extends beyond just capturing nearby galaxies. Our massive halo deflects systems that might otherwise approach on collision courses. The extended gravitational field acts like a cosmic traffic control system that prevents the chaotic encounters that once characterized galactic evolution. This maturation process is happening to large galaxies throughout the universe. As cosmic expansion spreads matter thinner, the expansion of space increases the average distances between galaxies over time. Systems that once orbited closely enough for frequent interactions now find themselves isolated by growing cosmic distances. The universal process means that the era of rapid galactic growth through mergers is ending everywhere, not just in our local environment. Observations of distant galaxies show declining merger rates throughout cosmic history. The violent universe of the past is gradually settling into a more stable configuration. The era of rapid galactic growth through mergers is ending, replaced by slower, more gradual evolution. Instead of dramatic transformation events, our galaxy's future will involve steady processes like internal star formation, stellar evolution, and minor mass accretion from the intergalactic medium. This transition resembles biological maturation, where rapid growth phases give way to stable maintenance periods. Our galaxy has reached structural maturity and will maintain its current configuration for many billions of years. The fundamental architecture we see today will persist with only minor modifications. This cosmic calm is only temporary. The period of stability we're entering will last for approximately 4 billion years before being dramatically interrupted. The approaching collision with Andromeda will restart the cycle of violent transformation, proving that even the largest galaxies are temporary structures in an ongoing cycle of cosmic recycling. The evidence scattered throughout our night sky tells this complete story of violence, conquest, and temporary peace. When you examine these stellar motions and chemical compositions, you discover the unfolding story of how our galaxy became a living composite built from ancient worlds. The next time you look up at the night sky, remember that you're seeing the aftermath of billions of years of cosmic assembly. Those peaceful points of light include stellar refugees from dozens of destroyed galaxies, each carrying the memory of their lost homelands in their chemical compositions and orbital patterns. Our galaxy has transformed from a cosmic predator into a mature system built on the foundation of ancient mergers. The streams of scattered stars, the retrograde populations, and the surviving dwarf galaxies all provide evidence for this systematic process. The Milky Way assembled itself through galactic accretion, incorporating neighbors to build the beautiful spiral we call home tonight. As you relax, let these quiet, vast motions sink into your restful mind. If this science helped you unwind tonight, consider subscribing for more evidence-based journeys into the cosmos. Good night.